In this section, we're going to be talking about the rates of return. And our first rate of return is called the holding period rate of return. And so in this example here, suppose I have a holding period for 1 year, and I have these, and I bought a stock at t equals 0 for $100. And I ultimately sell that stock at 1 year from the date of purchase for $105. So then my holding period rate of return is this formula where P1 is the point in time, the value at 1 year from now, the point in which I sold the stock. And P0 is time at now, t equals 0, which is when I purchased the stock. And then typically I would be any interest that is earned, but let's just say for the purposes of this example that there is no interest whatsoever. And so then I would divide that whole expression by P0, which is again the $100. So it would come up to a value of 5%. Now, suppose I had a rate of return for multiple years. How would I go about solving that? Say I had these three returns. In year 1, I had a return of 3%. In year 2, I had a return of 5%. And in year 3, I had a return of 8%. I could plug in this formula here, right, which is the holding period return for multiple years. And I would just plug in my return percentages, and then I would solve for that, which would get me a value of 16.8%. So that is typically what we call the holding period rate of return. In this next section, I want to talk a little bit about the arithmetic mean and what that means. But before we jump into what the arithmetic mean is, it's important to understand the difference between a population and a sample. So a population is, for example, the total number of values for a given set. So you could think about that as how many people are there in the entire world today, right? And that would make sense. Now, the sample is a subset of the values within a population. So you could think about a sample as how many people are there in Paris today. It is essentially a portion of folks that are representative in a population. So that's a very important thing to keep in mind as we look into the arithmetic mean. So the formula for the arithmetic mean is the sum of each observation over the total number of observations. And we'll look into an example here, but really the formula is what's listed here, with mu being the arithmetic mean and n, capital N, being the total number of observations in the entire population. Whereas the arithmetic mean of the sample is essentially the same thing with different variables here. So x bar means the sample, whereas mu was the population. And then small n indicates the number of observations in that sample. So let's look here at a following example. So what is the sample mean of the following returns? Suppose you have these 16 European countries with the returns listed here on the right-hand side of the table. If you follow the formula for the mean is, for the sample mean here, because there's only 16 European countries here, it's not every single country in the world, the return here is negative 31.25%. And one thing I did want to mention is a definition here of a deviation. A deviation is essentially the distance from an individual point to the mean. So you could think about the distance of the first point in Austria, which is negative 2.97, to the mean, which is negative 31.25. So there's a healthy distance from the mean for Austria. Now, why are deviations important? And deviations are especially important in financial analysis because they indicate the level of risk associated with a particular investment. And so you typically, the lower the deviation, the less risky an investment is considered. So now let's look at the median. The median is essentially the middle value of the sample. So in the example below, the median here are the two middle values because there's an even number of countries, and so you have to add those two and divide it by 2, and you get a value of negative 29.72. Now, the difference between the mean and the median. So let's suppose I have the following table here, right? And I want to calculate the mean of the PE ratios. Notice there is, that's the answer if you calculated the mean, but notice there's one PE ratio that's abnormally high, right, of 443.33, whereas the rest of them are essentially, around a certain number without an abnormal value within the set. So if you do the mean, you are essentially going to get a little higher inflated mean because of that one outlier. Whereas if you did the median, right, where you would list the numbers from least to greatest, and you would take the middle value, you get a median value of 19.07. And in this case, like we talked about, the 443 influences the value of that mean. So in this case, the median PE ratio tends to match the central tendency more than the mean. And again, that's the advantage. The advantage of the arithmetic mean is that it tends to use all the data points to compute an average, whereas the disadvantages are it's more susceptible to outliers. Let's look at the mode. So the mode is the most frequent value occurring in a sample or population. So suppose I have, the following credit ratings, right? The mode is essentially which rating occurs the most. And if I simply were to just take each rating and count them, I would find that BAA1 is the most occurring or has the highest frequency within the set here. Let's go on to the weighted mean. The weighted mean, and the best way to understand that is to essentially look at an example. Suppose I have a portfolio return for Canadian stocks, which is 60% made of stocks and 40% made of bonds. What is the portfolio return in each of the years here from 1998 to 2002? Well, I can simply use the weighted mean formula, which is shown here. So I have 60%, like we talked about, it's weighted in stocks. So my equities are a negative 1.6% for 1998, plus 40% for bonds, which is 9.1%, which equals 2.7%. And I can do the same for 1999, and you get obviously a much higher percentage because not only was your stock 31.7%, a much higher return than the negative 1.6 in 1998, the stocks are also weighted at 60%, whereas the bonds are weighted at 40%. So anyway, you get a higher number here in 1999 from a performance standpoint. 2000, it dipped a little. 2001, it dipped a lot. And 2002, it, was around the same as 2001. Okay. Let's look at another example here. Calculate the estimated average asset allocation for the following. So suppose I have the weights here and the average class return here, I can calculate the mean portfolio return using the weighted average as follows. Now, excuse me, the one thing I did want to call out is when we look at weighted average, we are typically looking at past or historical data. When we take weighted average of forward-looking values, we call those the expected mean. What is the expected outcome? Now let's look at my favorite method, especially in finance, to compute an average, which is the geometric mean. And the geometric mean is essentially the best way to determine a mean for an average over time, to determine an average over time. So the best way to understand that is to look at an example. So let's look at the following data, and then we'll calculate the geometric and arithmetic mean of the two funds below. So suppose I have these two funds. The geometric mean formula is shown here. I would divide the percentage here by 100 to get my values. And I would take the total number of observations, which in this case is 5. So I would take it to the 5th root of that and follow that formula. I would get 2.43%. If I did it for the arithmetic mean for that, I would get 3.54%. And same thing with the other fund. I could do the geometric mean at 2.53% and the arithmetic mean at 2.94%. This example, while great, doesn't necessarily do the best job of highlighting the value of the geometric mean as our next example here. So suppose I want to calculate the arithmetic mean and geometric mean for the following. Suppose I have a stock and my price at year 0 was $100. So that's the purchase price of my stock. 1 year later, the stock price rose to $200. And then finally, at the end of the second year, it comes back to $100. So my gain in year 1 was 100% because I've essentially doubled my money. And in year 2, I've essentially halved my money. So it was a minus 50%. If I did the arithmetic mean of that, I would get a return of 25%, which truly does not make sense because my purchase price was $100. And at the end of the second year, I was back to $100. Yet my arithmetic mean says I returned 25%. Whereas the geometric mean shows a value of 0% because there was no gain over time. And that is why the geometric mean is best to use for averages over time. The final one, the final mean we're going to talk about, or the measure of central tendency here, is the harmonic mean. And this is the best mean to use when investing an equal amount of money with varying share prices. So if you are one of those investors that just puts a fixed amount of money into the market each month with different share prices, you would use the harmonic mean to calculate returns essentially. So let's look at an example. If we purchase a stock worth $1,000 at $10 per share, and then at next month at $15 per share, the harmonic mean would be 1,000. So you'd have the fixed amount on your numerator and your individual share price on the denominator, and you would compute that, and you would get a value of $12, whereas the arithmetic mean would give you a value of $12.50.